In section 16.5, we're going to evaluate the triple integrals in this new coordinate system, cylindrical and spherical, and we may get to see some of these applications. We will also look at we're gonna come back to improper integrals for a pretty cool case right here. Well, okay, number one, the cylindrical coordinate. Well, you guys are already familiar with it because it's really the polar system in space. So what did we have for the polar system? Well, so in polar, we had a point xy that becomes r theta. That's because essentially we were plotting this point over a circular region. I mean, that's the simplest case, a circular region, but that's not, just know that that's not the only possible region. Of course, we can integrate over cardioids, over full hours, over many other graphs, you know. So, but how does that look like in space? Well, think about a circle in space. How does a circle in space look like? That generates a cylinder, right? With a height z, actually, it's going to look like, well, it's going to look like, so this, do you see this dashed circle right here? It's going to be the same dashed circle onto the xy plane. Let me do another one. Okay. Whoops. Like this. So really, any point on the cylinder will be simply, which is x, y, z, will be again r theta, but it's going to be at a high z rather. And that z is actually not going to change. The only thing that is going to change is the xy, which will become r and theta. Alright? So let's have a look at this new, so to speak, system of this new system. So again, a point P in space will be represented by a radius, an angle, where r and theta, where x and y are the rate are going to become r and theta, and z will simply be z. All right. That's what it doesn't change. Actually, if you look at the conversion formulas, they are exactly the same ones from the world of polar. There's no changes at all because z equals, it's still equal to z. That's it. All right? That's the new thing, but there's no change at all. All right? That makes it easy to work with. Okay, so let's convert the rectangular coordinate point 1, -1, 4 to cylindrical. Well, ignore the z coordinate for now and just focus on the xy. All right? Well, so let me graph the point on the xy plane. That is 1, -1. All right? So that's the point. Well, so what do we need to know? We need to get the distance from the origin to the point and the angle formed from the positive x-axis to the point, or to the ray formed by the distance between that origin and the point. I mean, if you look at 1, -1, I think the angle is very obvious, right? So I don't think you need to calculate anything. I mean, if you want to inverse tangent of y over x, but what's tangent of -1? Well, that's going to give us, what is that? What is that? I think you're finding sine or cosine of 45 degrees or so. No, we're looking for the angle whose tangent would be -1 over 1 or -1. But what would that angle be?
7 pi over 4.
7 pi over 4. Well, that's the angle we're seeing, but since we are evaluating the inverse function, there's a little catch here that's because the inverse tangent function is only defined between negative pi over 2 and pi over 2. So if we use the inverse function approach, that would be negative pi over 4. But that's fine. Use it is okay to use the 7 pi over 4 because, again, these points are 2 pi periodic, so it doesn't matter. So that'll be fine. That's negative pi over 4 or 7 pi over 4, either way. Okay, and what about the distance between the origin and the point? So just go about r equals to the square root of x squared plus y squared, which is the square root of 1 squared plus negative 1 squared. That's simply the square root of 2. Right? Okay, so that's the angle, that's the radius. We have everything to express this point in cylindrical. Okay, so that is 1, negative 1, 4. That equals the radius, which is root of 2, and the angle, which is, what's that? 7 pi over 4 or negative pi over 4, either way. So I'm going to do 7 pi over 4. And z remains the same. 4 is still 4. I highlighted that in the definition box. Right? Z doesn't change. Now let's do the reverse. Convert the cylindrical the point in cylindrical coordinates back to rectangular. Well, we have a freebie already because, okay, that is blank, blank, negative 5. So z doesn't change. Z remains the same. So what do we do in this case? Well, we know that x equals to r cosine of the angle, and where r equals to 3, and the y coordinate is going to be r sine theta. We can calculate this. That is x equals to r cosine of the angle. That is r, which is what? Is that a 3? Cosine of the angle, which is 5 pi over 4. And the y, which is r sine theta. That is 3 sine 5 pi over 4. Okay. Cosine of 5 pi over 4. So 5 pi over 4, is that in the third quadrant? They're both negative, right? In that quadrant, they're both negative. So that is root of 2 over 2, negative, root of 2 over 2, negative, but times the 3, that's a negative 3, negative 3. All right? And we got this. Negative 3 root of 2 over 2, and negative 3 root of 2 over 2. Alright, so that's going back and forth between rectangular and cylindrical, and vice versa from cylindrical back to rectangular. Alrighty. So now, what about surfaces in cylindrical? So that was point. The first two exercises were points. This third exercise is about sketching the surface given by this set in cylindrical coordinates. Because notice how the set is given. It's not given in terms of x, y, and z. So it would be easier if we were able to look at those variables and compare with our list of the quadratic surfaces and simply identify like this. However, we're going to take a different approach. In this case, well, so instead, we're going to create level curves. We're going to create level curves for different values of r. For instance, for r equals to 0, what are we going to get? Z equals to 2 times 0, which equals to 0. That's going to give us the horizontal plane, the xy plane, if you will. Z equals to 0. Let me do r equals to 1. So that is z equals to 2 times 1, which equals to 2. That is the equation of the horizontal plane at 1. Alright? R equals to, say, did I do 2? Okay, equals, so that z equals 2 times 2, that equals to 4. Well, what are we doing here? Because we have r's and we have z's right here. Those z's represent equations of horizontal, of planes intersecting in the z-axis, right? Not horizontal because it's space, it's different. But when we talk about r, what comes to your mind when you read r equals a number? is r really? What geometric shape makes you think of when you read r equals a number? Circle, right? So what do we have? What do we have here? R equals to 0. Well, that's a radius of that's a circle of radius 0. That's just the origin. We discussed that a few times before. R equals to 1, that means a unit circle. R equals to 2, that means circle of radius 2. All right? So we are really finding the intersection between the circle of radius 0, which is just the origin, and the plane z equals to 0. Well, I'm not going to draw the lanes really, so I'm just going to do, okay, I'm just going to do whatever the result for this will be. So this is just the origin. So the intersection between, what's that, z equals to 2 and r equals to 1, that'll be a circle, right? A circle of radius 1, but at a height of 2 units along the z-axis. So let me make it look like a unit circle like this. And then the circle of radius 2 intersecting with the plane z equals to 4, that'll be a circle of radius 2 at a higher height. So that's going to give us essentially this result. Doesn't that look a lot like a cone? Right? How does that look like a cone algebraically? Well, that's the level curve approach, you know, by giving some values to r. But again, what is r equal to? So recall that r squared equals to the square root of x squared plus y squared, to x squared plus y squared. And r equals the square root of x squared plus y squared. How about we substitute this here? That's going to give us then z equals to 2 square root of, what's that? X squared plus y squared. And squaring both sides, that's going to give us z squared equals to 4 times x squared plus y squared. Or z squared equals to 4x squared plus y squared. Doesn't that, or 4y squared, doesn't that look like the equation of a cone? Right? In rectangular, back to rectangular, rather than expressing it in cylindrical coordinates, which is in a way a lot simpler. So again, this is going to help us a lot just in simplifying this this kind of integration problem, which is the next, well, actually the next part is the integration using cylindrical. All right, so how does the triple integral look like in cylindrical coordinates? First of all, when are we going to use the cylindrical system? Well, number one, when they tell us to do so, because it's typically, number one, a suggestion to go about the problem in a way easier way, or just because that's the idea to get used to the new system. But under which circumstances? Well, so we would integrate using cylindrical coordinates when we integrate over cones, spheres, and of course cylinders, right? So let's say we're just given a bunch of exercises. They don't tell us what to do. If you're given any of those quadratic surfaces, the best choice is to go about cylindrical coordinates. Okay, so let's analyze this triple integral. So we may or may not integrate for volume. That is, again, recall that when f of x, y, that is the integrand, equals to 1, that triple integral will represent volume. If it's not equal to 1, well, that's something else. We will discuss that in the following section in 16.6. What about the limit? So number one, so when we change the coordinates from rectangular to cylindrical, dv, which is dz, dy, dx, well, because again, the cylindrical system, it's exactly the same as the polar, but in space, where the z is still equal to c. Remember, dy dx, what did that become in polar? So didn't that become r dr d theta? Which is here, r dr d theta. On the other hand, dz simply remains dz. So that's what the differential r dr dz dy dx becomes, r dz dr d theta. And well, I'm not going to go through the entire derivation of the differential, but you might remember how we use remember the New York style pizza slice to explain this thing about the polar rectangle to get the differential r dr d theta. Well, make it a Chicago deep dish pizza this time, you know. So what are we going to get? Do you see this? This part I'm shading here, it's still the r dr d theta, but that r dr d theta, it's being multiplied by the height z, which is just the portion of a cylinder. Rather than having a portion of a circle or a pizza slice, a New York style pizza, now we're getting a Chicago deep dish pizza to explain this, or to visualize this differential for the triple integral in cylindrical coordinates. There's really not too much of a change other than adding a third integral. That's all it is. Okay, how do the limits of integration look like? Well, again, for the results that we carry in this class, the outermost limits of integration, recall, they have to be constant values. So you end up getting a constant as a result that represents volume or maybe surface area or maybe maybe the mass, which we will discuss later. The second limits of integration are going to be a function of the outermost variable in this case, they could be simply numbers, or they could be functions of the outermost variable, which is theta. And last but not least, the very innermost limits of integration, the ones for z, that's actually three case scenarios. Number one, functions of both r and theta. Number two, or actually fifth case scenarios, or maybe just functions of r, maybe just functions of theta, or simply constants. It's possible that it's simply constant. Four case scenarios, all right? How about we'll look at one example. Okay, so use cylindrical coordinates to find the volume of the solid bounded by the paraboloid z equals 9 minus x squared minus y squared. Well, let's have a look at how this would look. Oh, in the xy plane. And again, whenever you see or whenever you read the xy plane, this means z equals to 0. 9 minus x squared minus y squared, look at the signs of the square terms. That would look individually like parabolas. If we were to get the traces upside down parabolas with the vertex at y or z equals to 9, 0, 0, 9, right? I believe though I have a GeoGebra solid here. Okay, yes, cylindrical, example 1. There you go. Yes, here it is. So that's the upside down cylinder. Okay, light. So, and it's bounded below by the xy plane, which is when we intersect it with the paraboloid, we get this as a result. We get rid of the plane. So let me get rid of the surface right here. So you can see the projection onto the xy plane, that is x and y. And again, notice how we would be integrating over a circular region. So what are we going to be looking at? Well, no longer at the upper radical minus the lower radical. Remember, we did that in the previous section just to set up the integral, because otherwise it would be a nightmare to evaluate. But cylindrical coordinates are going to be our hero here. In this case, we're no longer looking at that. We're looking at the radius, which is 3 units, and the angle spanned by the entire big circle, which is the entire rotation, that is 0 to 2 pi. All right. As far as the 3D perspective, okay, let me have the upside down paraboloid. This will simply be roof minus floor. What's the roof? Isn't that the paraboloid? What's the floor? Isn't that the plane z equals to 0? Yes, it looks circular because of the intersection with the paraboloid, right? Because we want a solid inside those two surfaces. Okay, so let me go back to the notes. I think we're ready to set up the integral. However, we still need to do a little bit of algebra to justify what we have in our GeoGebra solid. So guys, on the following take-home quizzes I will be giving you, I will still be providing this GeoGebra solid so you can easily set up the integrals, but still, there's some algebraic things you need to, or processes that you need to show to justify some of the limit. It's not just, oh yes, because of the picture, it looks like this other noise. There's some algebraic work that we need to do. So number one, again, if we set z equals to 9 minus x squared minus y squared equal to 0, that is, we're finding the intersection between the two surfaces. And the intersection between the two surfaces will give us the projection onto the xy plane. That is, set z1 equals to z2. Let me label this as our z1 and our z2. So 9 minus x squared minus y squared equals to 0. In the same way that you did it in calculus 1 to find the points of intersection between two curves, you said f1 equals to f2 or y1 equals to y2. But in this case, we're no longer finding points of intersection, but rather sets of points that is given by these equations in two variables. That means x squared plus y squared equals to 9. Doesn't that look like the circle of radius 3? Right? Now let me go back to the GeoGebra picture. Let me look at the xy projection. Doesn't that look like the xy, like the circle of radius 3? This one? Yep. So I mean, despite it's pretty obvious from the GeoGebra solid right here, we still need to get this algebraically, which is what we just did here. Okay, so let's plot that circle onto the xy plane. So you're not required to plot the solid, just the projection onto the xy plane. So circle, whoops, that is from -3 to 3, -3 to 3. That's a circle of radius 3. All right. What else do we need to do? So number one, we need to rewrite this equation in cylindrical. Well, polar cylindrical, yes. I mean, x squared minus y squared, that'll be okay. Z equals to 9 minus x squared minus y squared. I'm going to factor out the negative. 9 minus parentheses x squared plus y squared. And we know x squared plus y squared from polar, it's the same x squared plus y squared in cylindrical, which is r squared. Right? So that is, so our equation in xy terms becomes a simpler equation in terms of r, z, and theta. Well, in this case, we don't have theta in our equation because theta is varying. Well, it's not varying. It's constant. It's a number. Otherwise, if we had a different, like that circle shifted to the right or to the left, or arose or something like that, well, we would need to represent that differently. All right. So I believe we're ready to represent the domain. But I'm not going to write the domain in a, well, actually it's possible to write the domain in x, y, z, that equals, but that's the domain in rectangular. Well, x varies between -3 and 3. But what about y? So do you guys agree that from here we can get y equals plus or minus the square root of 9 minus x squared, where each plus and minus represent the upper semicircle and the lower semicircle respectively. All right? So that means y varies between negative square root of 9 minus x squared, and square root of 9 minus x squared. And lastly, what about z? I think this one is just bounded below by the xy plane, which is z equals to 0, and the square root, no, not the square root, actually the paraboloid 9 minus x squared minus y squared. So this is just the domain of integration in rectangular, but if you remember from the previous section, that would take us as far as setting up the integral. I mean, you could evaluate it, but it's going to be a nightmare. You don't want to, and we don't want to do that. Actually, the purpose this time is to convert to cylindrical and evaluate it in cylindrical. You'll see the power of this. So let me change the domain to transform it into r theta z. Okay? So r theta z. That means r, it's going to vary between 0 and 3 because there's no negative radii, right? From all the points on the circle go between 0 and 3. I know there's negative 3, positive 3, but it's a radius. What about the angle? Doesn't that span the entire circle, the entire rotation? That means 0 and 2 pi. And for z, well, it's bounded above by 0. That's the xy plane, z equals to 0. And it's bounded above by the paraboloid. However, I'm not going to write the paraboloid as 9 minus x squared minus y squared. Instead, I'm going to write the paraboloid as 9 minus r squared in polar coordinates. The equation represented with polar coordinates. That is 9 minus r squared. And we're ready to set up a triple integral in cylindrical coordinates that will calculate the volume inside. Bounded above by the paraboloid and below by the xy plane. So, okay, volume. To begin with, volume, that's the triple integral over the region D. That is dV equals to the integral from 0 to 2 pi. The integral from 0 to 3, and then from 0 to 9 minus r squared. This dv will become r dz, dr, d theta. Let me explain the limits of integration and their differential. So the innermost limits of integration, that is with respect z. So those could be, number one, constants or expressions containing either r or theta or both. In this case, it's just r. The second limits of integration, that is r. So this r could be constant because look at this circle. That circle has a constant radius that never changes. It's the same for all points. That goes between 0 and 3. But if we had a circle shifted to the right or to the left or a cardioid or something different, then we would need to write the equation describing that changing radius, that varying radius. And finally, the angle theta, there's no way, it's just constant. In this case, it's easy to see, 0 to 2 pi. Look at that integral. Imagine setting up a triple integral from negative 3 to 3, from negative radical to positive radical, from 0 to that vortex surface. Think of that huge integral and think about if we could evaluate it with the techniques that we know so far. So now compare it to this integral. Doesn't that integral look a lot simpler to evaluate? Okay, let's go for it. Integrate with respect to z. That means the integral from 0 to 2 pi and from 0 to 3 of rz evaluated between 0 and 9 minus r squared, and don't forget the dr, d theta. All right. So that means let me highlight the limits this time, because this upper and lower limit are going to be evaluated only for z, not for r. R is going to come later. Okay, upper limit minus lower limit upper limit minus lower limit. That is the integral from 0 to 2 pi. This integral from 0 to 3, r times 9 minus r squared minus 0, all right, the r d theta. Okay, so let me just distribute the r, 9r minus r cubed minus 0. Well, that's just 0. That's the integral from 0 to 2 pi. And from 0 to 3, 9r minus r cubed dr d theta. Okay? And then from here, let's see. Polynomial, why not? The integral from 0 to 2 pi, that is 9 halves r minus r to the 4 over 4, or rather 1/4, r to the 4th, evaluated between 0 and 3, d theta.
So 9 halves r squared.
R squared, you're right, r squared. Thank you. So that means, okay, the integral from 0 to 2 pi of, okay, upper limit, that is 9 halves 3 squared minus 1/4, 3 to the 4th, minus, how about big 0? Apply this to the lower limit of 0. This is going to give us a 0. Okay, close the brackets, d theta. And that is, okay, 3 squared, which is 27. 27 times 9 over 2, I get 81? No, that's not 27. That's 9. 9 times 9, 81. 81 over 2. No, hold on. I have simply the result for this. Well, that's 9. That's 81 halves minus 81 fourths d theta, which reduces to 0 to 2 pi 81 halves, right? No, fourths, 81 fourths d theta. Come on, integrate this number. That's simply 81 fourths theta d from 0 to 2 pi. That is 81 over 4 times 2 pi minus 0. That is simply 2 pi over 4. Is that pi over 2? That's 81 pi over 2 cubic units. All right? Way simpler than attempting to evaluate the integral in rectangular, guys. You don't want to do that. I mean, unless you wanted to take it as a personal challenge and set up a trigonometric substitution with two variables. It's not impossible. It's doable, but maybe not the most efficient way. That's just playing hero mode, essentially, right? If that's what you want. All right. Again, we want to set up another integral. Okay, evaluate the integral from -2 to 2, from negative radical to positive radical, and from this radical to a constant for an integral that has an integrand x squared plus y squared. So number one, this integral will no longer represent volume because that integrand, it's no longer just 1. It's something other than just a 1. And this time we're given the triple integral in rectangular. We're not given the problem in words for us to set up the integral. Okay. Regardless of how this is given, well, like in this case, it's given in the form of a triple integral. Just focus on the first two on the last two integrals. Focus on these two. That's going to give us the projection onto the xy plane, right? Because those two limits of integration are for y and z. Okay, let's see. Let's see what this represents. Okay, what is that for square root of 4 minus x squared? If you think about it, what does that represent? I mean, without changing to cylindrical coordinate, just geometrically, that square root of 4 minus x squared.
Square Semicircle.
It's a semicircle, right? A semicircle. Okay. So, upper semicircle, right? Lower semicircle. What about this positive 2? Doesn't that represent, positive 2, the x-intercept and another x-intercept, right? So, so that means we have the entire circle of radius 2, right? How do we know it's the entire circle? That's because of having both radicals as limit, the negative radical and the positive radical. So it would be a good idea to um, plot this circle. Okay, it's a circle of radius 2. Okay, it's a nice looking circle. Okay, that's negative 2 to 2, negative 2 to 2. So I think we can already see the limits of integration for r and theta, right? Isn't it that we're going to go between 0 and 2 for the radius and from 0 to pi for the angle? Alright? Okay. So, what is this? So what else do we need? Okay, what about the limits of integration for z? What is this? The lower limit. What is that? We've been working with that function before already a few times. Isn't that a cone? Cone. What about z equals to 2? What is that? It's just a plane, right? Let me see if I have a GeoGebra picture for it. I don't think I do. Oh yeah, I have it, I think. Yes. So we would have the following. We would have the cone. Well, this is the infinite cone given by GeoGebra, and this is the infinite plane z equals to 2. Well, let's see. So actually, I want to see the intersection between that cone. Let me get rid of this plane first. So that's given by the curve where it says 0. Okay, this curve right here, right? Did you see how this curve cuts the? That's where the two cut together. Okay. Well, I don't want the entire cone. I just want I just want this. No, I just want that. I don't know. That's not the one. Is that, where's that surface? Oh, this is the one. This one right here, that's the part of the cone that I'm interested in. Let me get rid of this part. And I don't want the entire plane. I just want this part of the plane. Let me get rid of this part too. Right? And the remaining curves, this curve right here, that would be if we slant that intersection, that circular intersection onto the xy plane, which would represent the projection. That so we can see the limits of integration. So that's the shadow, right? So that's the shadow. Let me get rid of this this one, that one, and is that this one, all right? So that's just the xy projection we did by hand, right? So again, it's important to do stuff by hand first and algebraically before, rather than relying 100% on this GeoGebra solids. Of course, they help us a lot, but again, we still need to do some algebra as well. Okay, I think we're ready to set up the triple integral. Okay, let's go back to the notes. So let's write the domain of integration. The domain of integration, I think it's pretty obvious from the limits. That is x, y, z, such that x varies between negative 2 and 2, y varies between negative radical 4 minus x squared, 4 minus positive radical 4 minus x squared, and lastly, z varies below by the cone, x squared plus y squared, and above by the plane z equals to 2. So I wouldn't even bother setting up the triple integral in terms of x and y. That's because we are expected to evaluate this using cylindrical coordinates. So that is, what's that? So r, theta, z, okay. Oh, we first need to write this z equals the square root of r squared. Isn't that equal z equals to r? All right. And the number 2 is simply 2. That's all it is. It's a height. All right. Okay, so the radius varies according to the xy projection, varies between 0 and 2. The angle theta varies between, again, 0 and 2 pi. And lastly, z varies between r and 2. We're ready to set up the triple integral. That is a volume. Oh, no, this is not a volume integral. This will be simply the triple integral, that is from r to 2, from 0 to 2, and from 0 to 2 pi. And careful, because what is this x squared plus y squared here in the integrand? What does that become? Just r squared, right? R squared. So that is r squared, okay, that times dz dy dx, which is another r dz dr d theta, okay. And simplifying the integral from 0 to 2 pi, from 0 to 2, that'll be another integral from r to 2, that's r cubed dz dr d theta. Again, think about just setting up this triple integral with the older limits in terms of x, y, and z. It's going to be another nightmare, right? Thanks to cylindrical coordinates, we get to evaluate basically Calc 1 type integrals, baby integrals. All right? All right, I'm not going to go through the entire integration process because it's very similar to that of the previous example. What we really want to see about these different exercises is how we set them up. We look at the solid in GeoGebra whenever provided, whenever possible, or in many situations we have to use our imagination. And then from our imagination, well, we can do the algebra given the equations of the surfaces, the curves and the like, so we can see what's going on onto the xy plane. And again, that's mostly what changes the setup. The evaluation is just same, and same. So after evaluating this integral, you should get 16 pi over 5. All right?